LAN interconnection. So that's what we want to do. How can we do that? What does it mean? Well, there are several ways of doing that. And apart from one case, which is the first one listed in this slide, which is the so-called repeater or hub, all of them share the same properties. So the repeater or hub is not actually exactly what we mentioned before when we talked about LAN interconnection, because it's not really allowing to extend beyond the limit of a single LAN. It's just a way of extending the cable length to ensure that you are able to receive properly, but still the limitation of the single LAN are the same. So it's just a kind of more or less sophisticated amplifier that allows you to enhance the quality of the signal that you receive, but the properties that you have are those of the single segment of LAN. So you may have one LAN with a single cable of 3 kilometers, one LAN with 3 cables of 1 kilometer each interconnected to a repeater. It doesn't make any difference at all, okay, in terms of performance. Starting from the other devices listed here, which are called bridge or switch when operating at layer 2, routers when operating at layer 3, or in general gateway when operating at higher layer protocols, we have a real network interconnection. So we are interconnecting through this store and forward device. All of them are store and forward device, whereas the repeater is not store and forward. They allow to really extend, interconnect a single portion of LANs, and on each LAN you can have, of course, the limitation of a single segment of LAN. The difference is just in the complexity of the device, because switches are acting and operating an interconnection only looking at layer 2 header, whereas the router do the interconnection looking at both layer 2 and layer 3. Don't forget that very often students come having in mind that the router is operating only at layer 2. Correct in the sense that the routing decision is made looking at layer 3, but by definition, in order to be able to access the layer 3 header, you must before run layer 1 and layer 2. So you are still operating at those layers, but at the end you will make your decision on the basis of what you see in the layer 3 header. So layer 2, layer 3 means the protocol at which those devices make their routing forwarding decision, okay? And then the gateway, even more complex. The bridge is used typically in a simpler scenario. The router allows you to have more complex interconnection patterns among nodes, as we will see in a moment. The key element is that all of them are store and forward. So whereas you send on a single channel, as we have seen before, the only delay that you have is the propagation delay, and of course the access delay, because before being able to access you may have to wait, you have to check the channel availability and all these kinds of things. That's called access delay. But once you have accessed the channel, the only delay that you pay to reach the destination is the propagation, because there are no intermediate nodes. When you put interconnection networks, you create an interconnection of LAN, you have intermediate device operating in a store and forward fashion, and you have all of the property of a store and forward network, packet switching with datagram service, which implies delay, in particular transmission and reception delay, and queuing delays. Okay? So that's the second point in this slide. So we are moving from a single channel scenario to a topology, because we are interconnecting several cables, several physical links, and that's called mesh topology. We are moving from a single shared medium to a mesh topology, interconnected through bridges, switches, routers, whatever. And as a consequence, since we have globally, if you look at that as a global network, more capacity available. Remember what is a capacity. Remember the first lesson we had on the topologies? We have defined the capacity of a topology. The capacity of the topology is the summation of the bit rate of all the links. That's the most we can hope to get out from this topology. If we are fully always using all the link capacity, the total bit rate we can get out is the network capacity. So in a single LAN, suppose that the bit rate of this single channel is 10 megabit per second. That's the basic Ethernet speed, the original one. At most, you can hope to get 10 megabit. If you have 3 segments of LAN, each of them running at 10, you can hope, since it's the mesh topology, to get out 30 if you are able to fully occupy all of them, and that depends on the traffic pattern. Okay, so we are moving from a single shared broadcast medium to, again, a typical interconnected network. Okay, now when we gain, well, we gain if the traffic is somehow local, as it is written here, Why? Let me see if I have a picture. I don't think so. So let me introduce this concept here. So suppose you have this scenario here. We have a network which is a single segment LAN in which you have n users. So this is a classical passive bus, the one we have seen up to now. Okay, you send, the signal propagates in the two directions, and everybody is receiving. Another way of, and we have a capacity C on this link. Another equivalent way of plotting this scenario is what we have called, if you remember, a passive star, in which somehow you can think that you take this long distributed bus, you collapse it in a single point, and potentially you make these connections, which typically here are of negligible length, much longer. Okay, so the length of this network here is bounded by, let's say, 3 kilometers. Okay, and here the distance that you obtain by taking the two longer cables, that's the longest distance that you travel on this network, should be as well bounded by 3 kilometers. Okay, those two scenarios are absolutely equivalent, just a different technological way, different cables that you use to obtain these networks. In the left-hand side, we have a passive bus or coaxial cable. In the right-hand side, we have a hub, which is a passive logically operating device, in the sense that you remember how does a passive star works. I generate a signal here, and this signal is propagated on any other link. That's how a passive, with no buffering. There is no buffering here. You just take the bits and immediately propagate on all the other output. Exactly what's happening here, right? You are propagating, in this case, in all the two possible directions. So those two topologies are absolutely equivalent. All of them have a capacity C of a single channel, because all of them are a network topology with one single channel. And if you have n users, you can hope at most to get out n over C, sorry. Oops. For each user, you can hope to get at most C over n. Divide fairly the capacity which C among the n users, under the hypothesis that all of the users are willing to send the same amount of traffic. Okay, that's the best we can do. We know that we are not going to be able to reach it because we have the problem and limitation of the access protocol. So it's going to be a little bit less than that. If we had an ideal protocol and all of the users are active in the same way, they will get C over n, each user. Okay, is it clear? The same if you have this scenario here, in which this device is a repeater, which means that whenever one user is sending here, the signal propagates, in this example, in the other two output ports. Absolutely equivalent. It doesn't make any difference. Everything works as if you had a single cable, because hubs or repeaters are devices which are operating at the physical layer, are basically sophisticated amplifier. What do I mean by sophisticated amplifier? Are devices which are receiving an electronic signal or electromagnetic signal, and instead of amplifying it, which would be in an analog way, which would imply amplifying the signal and the noise, they will detect the bit stream and regenerate the bit stream. So they are a regeneration point of the electronic or electromagnetic or optical signal. But at the end, everything works as if you had a single channel. The properties in terms of performance are bounded by this number here, C over N. Okay? Any question? Now, what happens is instead you have something which is an interconnection of LANs. Suppose that you have now an interconnecting device, which we call bridge, for example. So we have, sorry. In this example, we have 4 LANs, 4 segments. So in our example, the number of ports of this device is K equal to 4 in this picture, okay? And suppose that we have N users, which we subdivide fairly. So we have on each segment N over K users. And each link here has capacity C. Okay? Clear? Now, you see that we have now 4 links. So we expect to increase potentially the capacity of the network from C to 4C, or if you prefer, K times C. K being the number of ports, which imply also the number of links. Similar scenario in this more recent technology, if you have a switch here interconnecting 4 hubs. Which is how today we are actually going to cable networks. We are going to cable networks in this way here, just for a matter of simplicity of cabling. So we are avoiding coaxial cable, we are using twisted pairs. Now, both the bridge and the switch are store and forward device. Like the device we have seen up to today. If you remember, in any technology, when we talk about topologies, we had their store and forward device. You get the packet from one input, you store it, you look at it, and you forward on the proper output port, right? That's exactly what a normal interconnecting device does, and that's exactly what a bridge or a switch or even a router will do. Okay? Now, what's happening here? Well, as I said, we have a capacity which is K times larger, so we could expect somehow that we can increase this performance bound per user. This is the capacity per user, okay? C over N is the capacity per user. So since we have the same number of users but a larger capacity, we would expect to get, in the best case, a larger capacity. How much larger? By a factor of K. You have K channels, the same number of users, so we would expect to see that each user can get K times C over N. Okay, at most again, because then we have the problems of the real access protocol, which is not able to fully exploit the channel capacity C. But suppose we have this ideal protocol, okay? So we would expect to see something equal to C, K times C over N, again, for each user. Now, is this always the case? Yes or no? Who is voting for yes? You cannot abstain. Who is voting for no? Sorry? The total number of users is always N, and they are partitioned N over K on each of the K segment. So we have K segment, on each segment N over K users, so the total number of users is N. The rationale between this number is that if in the previous case with a single channel and N users we could hope at best to obtain C over N per user, since we have an increase in capacity in K, in the best case we would expect to see an increase in capacity per user by a factor of K. This is why I'm coming out with this number. Now the question is, we are always able to do that or not, or it depends or what? Remember that 90% of the time the right answer is it depends. So, okay, it depends on what? For the, sorry, can be a limit? A good point, that's interesting. In general, not. Now, the point is maybe the bridge of the switch can be a limiting factor in the network capacity. Whenever you put in your network a device interconnected to k links at a given speed, by definition, that device is, under normal operating condition, able to fully switch that capacity at full speed. Because otherwise nobody's going to buy it. So if you go to a seller and say, okay, I want to switch 16 port at 1 gigabit, the first thing that you do, you put in your lab, you load it with 16 generator at 1 gigabit, and you see what's happening in the output. If you don't get 16 gigabit, you get mad and you throw it away, okay? So nobody is going to sell a device with K ports not being able to switch at that speed, okay? We already have said, or we said already that there are situations in which maybe this device is running some particular upgrading facility or some application which is normally not running that may reduce the capability of that device. In that case, yeah, that may happen, but let's forget about this non-normal behavior. So under the normal hypothesis, that device, which of course increases the cost and the complexity of the network, because you have more cables, you have something that you have to buy, something that you have to power to make it work. So these are always drawbacks. But apart from that, from the performance point of view, normally they are not the bottleneck, especially in terms of bit rate. Of course, we already know that those devices will make it worse. What? The delay. The delay will be worse because you have to cross and to buffer and retransmit. That we know at the beginning, for sure. But in terms of bit rate, they should not put any limitation on your network. Yes? Almost. You almost got the point. Well, the real point is the following. Let's analyze in isolation. Let's analyze in isolation one segment here. Hello. So let's analyze this single segment in isolation. This is a network like this one, right? It's a single segment in which we have a capacity C, and we have a number of nodes which is n over k. So the capacity that each node will get is exactly k times C over n. So this number is what we would obtain in those 4 segments if they were running independently. Or if you prefer, if the traffic is fully local. Now, if the traffic is fully local, the bridge is not operating. And of course, each network is working as it was an independent network. And we have a network with the same capacity as this one, but with a reduced number of nodes. So you get better performance per node. So in this sense, we are able to reach this limit only if we have traffic locality. What does it mean? Nodes connected to the same segment exchange a lot of traffic. It's another way of saying what we said in general about topologies. Do you remember? It's a good idea to have nodes which exchange a lot of traffic close, because the path that you have to follow is short. If the traffic is local, the path length is 1 link. And that's the best scenario. Okay? As soon as instead the traffic, which is the worst case, the traffic is going through the longest possible path, we know that we will have a worse performance. Why I'm saying that what you said, that it depends on the number of users you connect to the hub? Because the number of users that you connect to the hub related to the traffic matrix can create unbalancement. If you have more net nodes on a given hub, suppose that the uniform traffic matrix hypothesis, we will have more traffic on that hub. So on that hub, the performance will be worse, and maybe on the other hubs, the performance can be even better than that. Okay, so it was not completely wrong. It really depends not only on the position of the nodes in the network, but more precisely on the traffic matrix that node exchange among them. Okay? So in general, that's the limit. So you can gain a factor of k, but in order to really be able to gain it, you need to have locality of traffic. In other words, if you want to have a network and partition it, it's a good idea to put clients connected to the same segment of LAN to their server. If you have several servers and clients refer to different servers, if you have to partition them, put the client with the server on the same segment of LAN, because at that point, huge amount of traffic is going to be local. Okay? It would be much worse. The worst thing you can do is to put the server or the servers to which everybody is referring on a single segment. Okay? So that's node distribution depending on the traffic distribution. Okay? Of course, if you have no idea about the traffic distribution, a priority what you will do, you would balance the number of nodes on each segment. That's, if you have no idea, that's the most reasonable thing to do, right? Because you have several links with the same ratio between node and links, and so that's a uniform distribution of nodes. Okay? That makes sense if you have no particular idea about the traffic exchange matrix. What's the worst case? Well, the worst case if everybody is sending toward a single LAN. If all of the traffic as a destination, a node in one LAN, what's going to happen? Excuse me? Collision you may have on each segment independently of that. It depends on the timing by which you may have collision even if the traffic is local, right? In general. You may have congestion. It depends. What's happening is that the whole network traffic at the end is going to go on this link, right? You have congestion only if the total traffic is larger than C. If it's smaller than C, there will be no congestion. But for sure, all of the traffic is going to run on this segment. Not only on this, but for sure also on this. Correct? And if it is happening, again, we will have at the end end users that have to share a capacity equal to C. So in the worst case, we will degenerate potentially to the same scenario that we have when the network is not interconnected. If the traffic is completely concentrated on one segment, at the end, all the traffic goes there, and you get the same performance you would get on a single shared link, because everything is going on that link. And so the performance are dominated, as you know, by the bottleneck link. This becomes the bottleneck link. All of the packets must go there, and all of the end users are going to share that capacity, and at the end, you will get out C over N. Is it clear up to now? We are looking at it here, it's exactly the same here. We are generating traffic toward the same node connected to a specific hub. On this hub, all of the network traffic is going to go, is going to be received. Okay? So we may gain by interconnecting up to a factor of k, where k is the number of ports of the interconnecting device, or if you prefer, the number of segments, independent segments, but only depending on how the traffic distributes in your network. In the worst case, we are not gaining anything. If all of the network traffic is going out through a server, the interconnection does not give you any advantage at all. So everything goes there, everything goes to this server, everything goes on that segment of LAN, and the bottleneck becomes C. Clear? Any question, any doubt? There should be a slide a little bit later that summarizes all of these informations. Okay, I hope so. Is it clear up to now? For everybody? Okay. Let me ask you another question now. So suppose that we are in the unlucky scenario. So we have an interconnected network and everybody is sending to the same destination or to the same LAN. It doesn't matter whether the destination is a single server or several of them, but everything is going there. Do you think that all of the users are treated in the same way here or not? Remember, here, as long as the protocol is fair, all of the nodes have the same access opportunity. So they will get really asymptotically C over n, a little bit less because we have the collisions, but in any case, whatever is left from C is fairly shared among everybody for sure, because everybody has the same access of chance of access, okay? And here, suppose that everybody is sending on this LAN. It is really true that every user is getting C over n or not? And if not, why not? Yep. Yes, that's the point. So all the traffic goes here, right? Now, if you analyze this network, you have several users. How many? N divided by K plus the bridge or the switch, it doesn't matter. And this bridge represents through 3 ports the other K minus 1 divided by K N users. Sorry, not divided by K. The other K minus 1. Oh, N. No, it was correct. K minus 1 times N over K users globally. Okay? All of those users access this segment of LAN through the single transceiver, right? They may generate a huge amount of traffic. Those packets goes to the bridge, they are buffered, and one after the other one will access the link. But all of them have only one transceiver available, as all of the other nodes. So what's going to happen in this segment is that actually you have N over K plus 1 transceiver. The number of active transmitter is N over K plus 1. Correct? And those transceiver will get fair share of C. So all of them is getting C divided by this number. But C divided by this number is for each of those nodes and for the bridge, which means for all of the other nodes together, they will get, so all of the other nodes, which are the vast majority of the nodes in the network, will get the same bit rate of a single node here. Why? Because that's a mesh topology. So the performance that you get depends on the path that your traffic goes through. Whereas if you have a fully multiple access scenario, you share fairly. In this case, you have a partly, you see, you have a multiple access here, and then you have a multiplexing in this buffer for all of the other users. Yes? I will repeat it, okay? Let me use a new slide. So if you analyze the case in which everybody is sending on a single segment, what's happening is that we have all the traffic going on a single LAN, correct? And on this single LAN, we have N divided by K users, because we have distributed them fairly among the K ports, and the bridge, which has K minus 1 links, to which of this link we have N times divided by K users, right? We have N divided by K here, N divided by K, N divided by K. So the total number of users which are accessing this LAN through this single transceiver is K minus 1 times N over K. 3/4 in our example, right? 1/4 in the segment and 3/4 in the other 3 segments, if K is 4. Okay? Now, those 3/4 of the users have exactly the same access opportunity when transmitting on this link as any of the other single nodes. On this LAN, you have N over K plus 1 transmitter and receiver, correct? And they are fairly sharing this capacity C. So each of those users here get C divided by n over k plus 1. Correct? If the protocol is ideal, etc., etc., etc. Unfortunately, this number is the same for all of these users here and for the bridge, which means that all of those users, k minus 1 divided times n over k, are getting the same bit rate together as one node here. Because all of them get this capacity here. So the capacity that each of those nodes gets is this number divided by k minus 1 times n over k. All of them have a multiplexing stage here. You put all of the data in this buffer, and then you have only one access opportunity. So you are concentrating a lot of traffic on one single transceiver. And unfortunately, all of the nodes which generate this traffic have only this access opportunity. Of course, if you change the network segment, the scenario will be reversed. The type of nodes which will be in favor position will be different, and the nodes which are not favored are other ones. So globally, it's fair. But when you examine a scenario in which you focus as a destination on a segment, there is a strong unfairness, which you would not have if you had a single multiple access network. So at the end, you have the same capacity, because the capacity is C, because everything goes on this LAN, with an unfair distribution of this C among nodes. So it's going to be even worse with respect to the single LAN. Is it clear? We are in the scenario in which we don't gain anything, and furthermore, we are treating nodes in not in a fair way. Why? Because we have a mesh topology. And in the mesh topology, the bitrate that you get depends on the path that you follow to reach the destination. There are some nodes that have a path which is very short, and all the other nodes have this much longer path, and they got worse performance. Okay? It's more clear now? You have any question? It's even worse than that. Why? Because if you had a shared single LAN, you don't have packet drops. You may have collisions, but if you detect, and you suppose that you detect collision, you will retransmit. So if a packet reaches the destination, unless, let's forget about bit errors, okay, it will be received. Here you don't know, because if the traffic which is going in this bridge is very large, you see that you have a potential congestion, as some of you said, right? You have 3 links, which may generate at speed C, and only one output link, because everything has to go here. So if for some reason the amount of traffic coming from these 3 links exceed the output link capacity, we really have congestion here. And congestion implies that this buffer will fill up, and when it's filled up, you will start dropping packets. So now we have an interconnected LAN in which packets may be dropped, which means packet may not be received, which is not typically what's happening in a single segment of LAN, in which we assume that packets are typically received. Why? Because it's becoming to be a packet switched network. And in packet switched network, we have buffering. We know that if we don't control the traffic, we may drop packets. Okay? More clear now? Which is the limit in this process? Or if you want, how far can we go deep in interconnecting a network, in partitioning it? Well, the limit is when k becomes equal to n. When k becomes equal to n, you have a bridge with n ports and with a single user per LAN. Right? If you prefer to, you may have a switch and to the switch, you have a direct interconnection for all of the nodes. That's the limit. Remember that when we have the potential capacity increase is K C over N. But when K is N, each user can get C. Why? Well, you have a devoted link. You see, there is a single LAN. On each single LAN, there is a single user. So you can send, and basically, if you are the only user, there is no collision, which is possible, correct? So that's the limit. That's called switched LANs, fully switched LAN. And actually, each user can have a capacity equal to C. We have one cable per user. Now, are we able to reach and to get this limit? Again, it depends on how the traffic distributes. Because this node has a channel at speed C to reach the switch, but then whether this C will translate in a real C or no, it depends on where this traffic is going to be. Because again, in this example, if we take again the worst case, if everybody is sending to this node, all of the nodes have a capacity C to reach the switch, but then all of the traffic goes on the output link at capacity C. So you have a potential huge congestion, because you can have an overload of n-1 on that output link. And so at the end, again, if everybody is sending to only one node, since the link connected to this node has a capacity C, you will share the capacity C among the n nodes, and you don't gain again nothing, because the traffic is non-local. Okay? Let me focus on this example here for a moment, which is something in which you can range for a capacity C over N up to a capacity C per node. So when we get C over N, let me replot this switch having inputs here and outputs here. You know that we can define always the switching node in two ways, right? In this case, we have bidirectional links, and in this case, we are separating each port in its input part and output part. So this is a single port, single interconnection point like here, okay? This interconnection point here is divided here and here, okay? This is closer to the physical representation on the left-hand side. This is a logical representation. Now, is it very clear here, I guess, that if everybody is sending to the same output, you have a huge bottleneck here, right? You have a link at speed C, which is loaded by n-1 times C, potentially. You have n-1 node, supposing that the same node is not generating toward himself, which typically does not make sense. But all of the other one, n-1, may load this link at capacity D, which is n-1 times C. So we have an overload, potential overload, and the congestion by a factor of n-1. And that's the worst case, in which you don't gain anything. We go back to C over N, roughly speaking. So we are coming back to the case of a single LAN. Okay, that's the worst case. The best case, well, it does not make many sense in this scenario to say that each node is sending to himself, right? Normally you don't do that. But just to give you an example, suppose that each node is sending to a different destination. This is just an example. In this case, every node has a capacity C to reach the switch, and the destination is on a different output where you have a capacity of C. No problem. Every node is getting C. You are perfectly distributing the load on all of the links. All of the links may be fully loaded, and you have no contention, and then you go back to this maximum value of C per node. That's an example of a traffic pattern in which you get the maximum from the network. Every node is sending to a different node, to a different destination. Okay? Clear? What's happening if the traffic is uniform? What's happening if the traffic is uniform? Wake up! What's happening if the traffic is uniform? This is one of the cases in which the answer "it depends" is wrong. Because uniform traffic means what? Every user toward any other road, right? So it means that basically this user here, which is reaching this node at capacity C, is generating toward the n output port how much? How much traffic goes from this input to this output? C over n, right, for any of those. And any output is receiving how much from any input link? From any input link, from any input port, how much you receive here? C over n. So you have a total of C on each input, which distributes as C over n for any output, and you have C over n coming from any input for every output. So it's a fully loading input and output, which capacity C is a full distribution again. So for uniform traffic, again, you reach the maximum. Okay? Is it clear? No? Yep. Okay. C over n if you consider that node can generate it over themselves, or is C over n minus 1 if you assume that this is not possible. But this is a detail. Let's take it for very large n, it doesn't make any difference, okay? The point is that you generate C, you distribute this C uniformly among any output port, so that any output sees one portion, which is C over n, from any of the n input. So the total that you receive on any output is C. The total you generate is a C, and so you are fully loading any input and any output, like you do in this example. So in the case of uniform traffic, again, that's another type of traffic in which we get C over, sorry, not C over n, C, the maximum possible traffic. Okay, and again, how much do we get? It depends on the traffic distribution in terms of bit rate. Clear? Now, if this is clear, let me go and see if there is this summary slides, then we will see some details. So these are the two slides that you should highlight. Slide 214 and slide 215, which summarize, I hope, what I said, actually adding something. So throughput performance may increase. We have seen how and when. We have more space diversity, we have more capacity, but only if we are able to exploit some sort of traffic locality. If the traffic distributes well, we get it. If the traffic distributes badly, we may not gain any advantage. Okay, that's what we have said up to now. We introduce store and forward delays. So in our example, we had only one interconnecting device. You may have a cascade of them. It depends on how do you interconnect your network. From the performance point of view, it only depends how many independent links we have. You can have one switch, 3 switch, 5 switch. At the end, if every user is connected to a switch, from a point of view of network capacity, we have a capacity that is enough to provide C to each user, okay, which is the maximum. However, the more devices you cross, the more store and forward delay you pay, okay? And remember that they also may imply queuing delay. That depends on the traffic pattern. So the delay are worse than a hub or are worse than a single cable. An interconnected network has worse delay, okay? The store and forward delay is non-negligible because in a single network, if you think about it, the only delay we have is propagation delay, correct? Right? And that we pay in any network. You pay it in a single line, you pay in an interconnected line. If the distance between A and B is 2 kilometers, you have this propagation delay. You can have 10 segments, 3 segments, 2 segments, it doesn't make any difference. Okay? So the propagation delay is constant in any type of network. In the interconnected case, you add store and forward delay. Now the question is, this store and forward delay is negligible or is significant with respect to the propagation? And the answer is yeah, it depends, maybe acceptable, it depends on what? No. Arg! 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 You said, no, it's not true. You said three wrong things in one sentence. First, propagation delay is one issue. Store and forward delay is another issue. Queuing delay is a third issue. Shut up. Okay, even worse. Processing delay is a further fourth component. Okay, so first assumption. Processing delay, we said many times, we assume to be negligible. Remember why? Okay, why? And why it is negligible? Why? I made a very short link. The propagation delay is very little. Why is becoming negligible? I thought I told you already. I'm not 100% sure, so I will repeat it. Yes, somehow yes. Again, for the same reason why I said before, if you have a switching node that is sold to be able to support 16 port and 10 gigabit per second, okay, you must support this traffic. Of course, if it is admissible, it means there is no congestion. Now, if there is congestion, there is no device that can solve the problem. Too much traffic want to go to a given output, there is nothing you can do. Okay, so if you load your switch, all the inputs with load 1, and everything all the traffic is going to one output, there is no device that can solve this problem. Okay, that's a networking problem. So if you load this, all of these links are loaded at one, but the traffic that you generate goes on one output link, is not the problem of the device. It's a networking problem. It's the traffic distribution problem. There is no device able to solve this problem. Clear? So you have to load your switch with what is called admissible traffic, something that the switch should be able to transfer. In this case, the switch is not able to transfer it because you are overloading one output. So one example of admissible traffic is, for example, just one example, there are many others, is the uniform traffic case. If the traffic is uniform and you are fully loading the input, through the distribution among all the outputs, we already know that any output is fully loaded, exactly at load 1, and the switch sold to be able to support n port at that speed should manage that. Clear up to now? Now, what does it mean in terms of processing of the packet, being able to sustain the traffic? It means that you are keep receiving on each input a sequence of back-to-back packets, right? That's fully loaded. One packet, one packet, one packet, one packet. If the load on the link is 1, you are keep receiving packet one after the other one, right? Don't say anything, but at least make this. Okay, good. So you have a full link loaded by packet, and then the packet and the other packet, etc., etc. Good. Suppose that the packet size is fixed for simplicity, and suppose that all of the packets are received at the same time from any input. It's not exactly like that, but doesn't matter. So what's happening in this device? At any packet time, because if the packet size is fixed, we have a packet transmission time, which is a fixed value for all the inputs, you will receive how many packets? N, correct? 1 per input. So we get n packets per slot. Let me call it slot time. The slot time is the packet transmission time. Okay? So if we want to support this traffic, we have to get rid of those end packets in one slot time. What does it mean, get rid? Read them at the input, process, store, process, make a routing decision, and move to the output. Because if you don't do that, in the next slot, you will get end packets. If you have accumulated some delays, you will not be able to sustain this traffic for sure. So if this device is able to sustain the traffic that we have said, it must be able to process n packets, where n is the number of inputs and outputs, okay, at transmission time speed. So in one packet transmission time, we must be able to process n packets, which means receive them, read the header, move to the output port, and queue there. Okay, so that's why we state that the processing time is negligible. It's largely negligible with respect to the transmission time. So we can assume that we don't have any further additional processing in this node with respect to the delay that we have in reception and transmission. That's the assumption that we make. That's why the processing delay we forget. Okay, it's clear now, more clear? Okay, so processing delay is negligible. Which other components of the delay we have? We have the queuing, but the queuing we don't know. It depends on how many other packets are generated by the other users. And then we have the store and forward delay, which is something we add only if we have the switch or the bridge. Now the question is, by adding a switch or a bridge, and we increase for sure by this delay, which is the reception and transmission delay, let's forget about the queuing, let's neglect the processing. This additional delay with respect to the propagation, it is large, it is little, it is equivalent, is negligible, it depends. You started very well stating it depends. Any idea? Okay. If you, you should remember something to be able to answer to this question. It is what I said, I think, 1 hour ago, more or less, in which I said that the minimum packet size, in terms of transmission, we are talking about transmission time here, is at least twice the propagation delay. You remember that? In order to detect collision. So the smallest packet implies a transmission delay which is twice the propagation, and that's the 64 bytes packet. The largest packet, and normally we prefer to send large packet because of the overhead ratio. If we can, we have to do a huge file transfer. We always try to create packet as large as possible, is more than 1 order of magnitude larger than that, right? Is 1,500 bytes. So the delay that you pay, the minimum delay that you pay because you cross a switching device, is at least equal or typically 1 order of magnitude larger than the propagation delay. So the delay that we add is significant. And we are neglecting the queuing, because this is multiplied by the number of packets that you find in the queue. Okay? So in general, the additional delay is not negligible, it's significant. Clear? With respect to the single LAN case in which you have only the propagation. And it's also written there, actually. The transmission time of a minimum packet size is at least twice of the propagation delay, and typically we generate large packet, not small one. Okay? We may have potential packet losses when queues filled up. We have seen an example before, right? If we are sending a lot of traffic toward a given output link, that bridge, that switch saturates if there is an excess of traffic, the queues fill up, and after a while you may have packet drops. And we have unfairness in resource access. We have seen that example, right? All of the other users except the one connected to this LAN are very penalized when accessing this specific link. Okay? That's a summary of things that we have seen and we have said. I don't know why I'm not in presentation mode. Sorry. Doesn't make a big difference, I guess. But okay? So that we said. That's the summary of what we said in, I think, almost 1 hour. Okay? Hope that now, after the discussion and the notes is more clear. Any question about that? Everything is clear, or you are so desperate that who cares? Or it depends. Okay. I bet the majority would vote for the second one, unfortunately. Okay. Think about it. If you have problems, you can come, we can discuss it offline, no problem. Okay. We didn't specifically say that. It's kind of direct consequence of what we said. We are slightly moving from what is a pure multiple access network through something which is a mix of multiple access and multiplexing, up to a point in which you have only multiplexing. Here it is the picture. In this picture here, in the top of this graph, we have multiple access among these nodes and the bridge is a multiplexing point for all of them. Okay? If you move to this scenario here, there is no multiple access anymore. It's just full multiplexing. If you wish, there may be some multiple access between the node and the switch, because they are sharing a link. If this link is, as normally it is, full duplex, which means one bidirectional link, two unidirectional independent links, there is no possible collision, because on every link you have one transmitter and one receiver. So that's a fully multiplexed technology. There is no multiple access anymore. Okay? It's like a point-to-point link, like frame relay, ATM, anything. It doesn't make any difference. One transmitter, one receiver. There is no multiple access. Correct? Everything is multiplexed. If you have a fully switched network, it is a fully multiplexed one, which is written here. If it's full duplex, which means bidirectional link, okay, independent unidirectional, Ethernet becomes what? Well, there is no multiple access anymore. But if there is no multiple access, the MAC protocol, the CSMA CD with one persistent version, etc., becomes useless. Because there are no conflicts by definition. There is only one transmitter. We are building a LAN in which there is only one transmitter per LAN. So by definition, there will never be a collision. And so we can use Ethernet, but at this point, Ethernet becomes another framing technique equivalent to frame relay, ATM, ISDM, etc. It's a point-to-point technology. The limitation on the packet size becomes useless because it's a point-to-point, there is no collision. So we still have in our cards, even if today most of the LANs are fully switched, there are some cases in which you can find some hubs, okay, but most of the LAN today are fully switched. We still have an Ethernet card which runs CSMA TD, collision detection, everything that we have described, but basically it never activates anything because there will be only one transmitter sending data, so there will be no collision, no need to detect anything, no other users using the channel, so the CSMA, the carrier sense, will always tell you that the channel is free, etc. So we are running and using Ethernet frame as another alternative framing technique with respect to ATM, frame relay, etc. We keep the compatibility in terms of card because you may end up using this card instead in a half duplex LAN, which is a multiple access LAN, in which case you have no problems because you run the protocol, you do everything you have to do in a multiple access network. But typically today, this is not the case. So Ethernet becomes a framing and transmission technique alternative to LAB-B, LAP-F, ATM, whatever. The MAC layer becomes basically useless in terms of coordination for accessing. It is useful because in the MAC header we have the error detection, we have the packet delineation, which is packet separation. All of these features and addressing are used, but not the medium access control protocol. The protocol is not needed anymore. Okay? And the physical distance limitation, which were originally imposed by the quality of the media, because of course you cannot have a single cable of 20 kilometers working properly. But more than that, by the protocol limitation we have seen, because we want to have we need to have a minimum packet size, and as a consequence, the network size should be not too large, etc., etc. Now becomes, if you are using only full switch technology, becomes completely open. You can send a packet of any size because you have no issue of collision detection. So the packet size limitation is not needed anymore. Okay, and this is the current scenario. As a last note, we must say that by partitioning the network, you are partitioning naturally the traffic on a single segment. So it may be easier to put some filtering or protection on the switch port, whereas if you have a fully multiple access technology, there is no central point that can control the traffic, right? Every user is doing whatever he wants. And so any type of management, traffic separation, security enforcement becomes very, very difficult. If instead you have a mesh topology in which the traffic is going through your switching device, you can put any algorithm you like in your switching device and you can do management, partitioning, filtering, whatever, security, and these kind of things. Okay? Which is a significant additional advantage of point-to-point technologies. Okay? Now, clearly, the fact that you are running in a multiple access scenario or in a multiplexing scenario has a direct implication on the performance and as a consequence on the quality, because you are moving from a network with small capacity to a network with larger capacity for the same number of users. Okay? If you want to exploit this, you must somehow control your traffic distribution, like in any packet switching network with mesh topology. Okay? These concepts are fairly important. So I know that they are not easy. I mean, this 1 hour was very dense of information, and especially information that is all needed to fully understand the problem. So my suggestion will be, if you have to go back to some of classes to review some things, this is a good lesson to review in order to make sure that you really have understood this concept, because I mean, we have seen them in the context of Ethernet, but these are very, very general concepts, okay? Very general. How you are sharing resources, whether you have multiple access or multiplexing, this is what we are talking really about here, besides of the format packet and the Ethernet or the names or the technology, okay? Different way of dealing with network depending on whether the channels are shared or not. That's the point. What time is it? Oh boy. Yeah, there are some details here. You may go through them. They're not so critical from our perspective. Let me go quickly through some of them, and then maybe we can finalize some of them next week. So this is in terms of protocol architecture, what a repeater or a hub is doing is just operating on bits at the physical layer. So you get some bits and you propagate them on the other port. So there is no storing forward. This is just, as we said, not an interconnection. It's just an extension of the cable length. Whereas if you start, and this is written here, to be completely honest, you may introduce some slight delay in the repeater because you have this process of detecting bits and retransmitting bits. So you may introduce some few bits of delay, but just few bits for this processing purpose, but it's negligible, it's typically negligible. Bridge or switch, these are two different terms. From a functional point of view are the same things. Today we are always talking about switches, but because bridges were something a little bit older in terms of technology, they were coming when we had networks cabled through coaxial cable and not through twisted pair. Bridges were able to support different access protocols like Ethernet, CSMA, CD, token ring, token bus, etc., whereas switches are only Ethernet based. Okay, but apart from that, they are exactly the same type of devices operating at layer 2. So you make your routing decision, your forwarding decision only at layer 2. Whereas, and this is summarized here, and In particular, the peculiarity of bridges or switches is that they are transparent to users, which means that apart from the performance, from the behavioral point of view, the behavior in terms of building the packet format, putting the addresses, and all these kind of things, you have the same process at the host, whether you are connected to a multiple access hubbed network or to a switched one. It does not make any difference at all. So you don't perceive as a user, as a hub, as a NIC, you don't perceive whether your network is hubbed or switched or partly hubbed or partly switched. It doesn't make any difference. You may have an effect on the performance, but that's another issue. And in particular, bridges and switches do not modify packet content, especially exactly because from the user perspective, there should be no difference in terms of behavior from the one that you had on a single segment. So when you have a single segment, you generate a packet with your source address, the destination address of the device to which you want to connect to, and that's exactly the same thing that you do whether there is a switch or not. It does not make any difference. As a consequence, since the receiver must receive exactly that packet, you must not modify any packet in the switch or in the bridge. Clear? The router, the difference between a bridge and switch is just in terms of technology, as I said. This is how modern LANs are created. You connect through a twisted pair all of the offices or of the rooms here in a given point, typically at the end of the corridor. And here you have connections that may be through hubs or directly to the switch. This is the star we have seen before. If the central point of the star is a hub, that is a passive star behavior, one channel. If the point is a single switch, that's a fully switched network, that's an active star. And if you go back to the first slides of the first lesson, the passive star is equivalent to having C equal to 1 channel. The active star is equivalent to having C equal to N channels, 1 per user. Okay? And where is the router? Here. There is no slide for the router. No. Okay. And well, the router, I don't know why there is not a slide, sorry. I missed one slide. Sorry for that. The router is similar in terms of protocol architecture, but it's operating at the network layer. The routing, the forwarding decision is made looking at layer 3 address and not a layer 2 address. Okay. Now, what is missing in this picture, but we will discuss quickly next. It's 5:25, right? So we have to finish, okay? Next week is how a bridge is able to do a forwarding basically without running a routing protocol. Because you know that in a mesh topology, you need to run a routing protocol. You need to know which are the paths, you need to make the selection of which is the best path and all these kind of things. Bridges don't do that, are able to forward in a proper way, and we'll see what proper way means, without the need of running a real routing protocol. And we will see how this is possible and why. Okay? And again, this will have an impact on the performance that you can obtain from a given mesh topology.